Great, thank you, and good to see you. And yeah, also, of course, really sorry that I couldn't be there in person. Would have loved to be there, and actually quite jealous of those of you who are there now. But maybe next time. And it's at least very good to see that this hybrid format seems to be working quite well. That's really really good. So yeah, we're switching topics quite a bit now. So going to ultra high energy cosmic rays. And so basically, yep, there we go. So basically every presentation on, or almost every presentation on cosmic rays starts with a figure like this one. So yeah, I'm sorry for not being very original at this moment. But yeah, it's a good point to start with. So this is the energy spectrum of cosmic rays, and it shows that it spans a really very large energy range from GeV energies up to 10 to the 20 electron volts. And what you can see as well is roughly then the amount of the rate of cosmic rays at the different energies. So we at the lower energy range, we have roughly about 1 cosmic ray per square meter per second. So this means that you can actually send up a spacecraft or a balloon, something like that, into the sky and detect these cosmic rays directly. But if we now go up to higher energies, and we see 1 cosmic ray per square meter per year. So there, what you generally do is build ground arrays, so detectors on the ground, and actually see the air showers that are produced in the atmosphere that are produced by these cosmic rays. And then if you go to the highest energies, you get to 1 cosmic ray per square kilometer per year. So in that case, you really need these huge arrays to be able to see these particles, or at least a significant number of these particles. So what you can also see is there are several features in this energy spectrum, or we have the knee around here and the ankle at the highest close to the highest energies. And generally speaking, or the general picture is that cosmic rays below the knee have a galactic origin, while the cosmic rays above the ankle have an extragalactic origin. And somewhere in between, there's a transition from galactic to extragalactic. And for this presentation today, I would like to focus really on this highest energy part, so the ultra high energy cosmic rays, where we kind of know, or can at least assume, that they are extragalactic. And for these cosmic rays at the highest energies, there are 2 main experiments that detect them, which are the Pierre Auger Observatory in Argentina and telescope array in the United States. So I will, during this talk, mostly focus on the results from the Pierre Auger Observatory. This is just because the Pierre Auger Observatory is about 4 times larger than telescope array, so just collected more statistics. But I do also want to mention that it's actually really interesting to also look at the telescope array results, also because they are in a different hemisphere, and the telescope array looks at the northern hemisphere, while Auger looks at the southern hemisphere. So they potentially look at different sources, but they also see a slight difference in the spectrum. So this, the spectrum that you see here, and that's a zoom in of the previous figure, but now multiplied by E cubed instead of E squared, just to make the features in the spectrum more visible. And you see already here that there seems to be a difference over the whole energy range. But what is not shown here are the systematic errors over this on these spectra. So if you now shift them within their systematic errors, then you can make these spectra fall exactly on top of each other in the low energy range. But at the really highest energies, there are still significant differences, which cannot be explained just by systematics. So this is also something quite interesting to look at. But let's see, maybe after time to get into this a bit more at the end of in the discussion session. But yeah, for now I'll focus mainly on just on the spectrum of the Piaget observatory. So if you zoom into that one, then we see several features in the spectrum. We have the angle again here, and so all these features are just changes in slope of the spectral index, basically. So with the angle, we have a so-called instep here, which changes where the slope changes. This is a relatively new feature or newly discovered feature, which was first reported last year. And then we have the suppression at the highest energies, where we have a strong drop-off in the flux. So now one of the interesting questions here is how to explain all these different features, and that's one of the things I will get into later. And one other thing, besides this energy spectrum, which also needs to be taken into account when looking at ultra-energy cosmic rays, is the composition of the particles. So this is shown in these bottom right plots. So generally speaking, this composition is determined by measuring the distribution of a quantity called X max. And you see here, this is the average of X max, and this is the spread of X max, measured by the Piaget observatory as a function of energy. And these red lines are models for pure proton composition, and these blue lines are models for pure iron composition. And you see that the data lies somewhere in between, where if you look at the energy, here we are roughly at the ankle, and here as well. So basically at the ankle, you have a very light composition. Well, if you go up in energies, you get heavier and heavier, closer to iron. So you get heavier and heavier composition, and you get a mixed composition, perhaps in between. So one of the big questions in this field is, of course, what are the sources of these ultra-energy cosmic rays? Unfortunately, we do not know that yet, but what is very encouraging is that we have that we're starting to detect a significant anisotropies in the arrival directions of ultra-energy cosmic rays. So the Piaget collaboration has reported a dipole at around 8 eV, so this is right above the ankle. And what is good to see, and this is shown in this figure, and this plus here shows the direction of this dipole. And what is quite interesting to see is that this dipole points away from the galactic center. So this figure and both these plots are in galactic coordinates. So the galactic center is in the middle. So this dipole points away from the galactic center, which is another indication for that the sources of these ultra-energy cosmic rays are actually extragalactic and do not come from our galaxy itself. And if you then go to higher energies, you can also see intermediate scale anisotropies, which are shown here in this figure. And here, yeah, at higher energies. So the difficulty about discovering what the sources of these ultra-energy cosmic rays are is that these are charged particles, so they're protons or iron to iron nuclei, completely ionized, so they get deflected in extragalactic and galactic magnetic fields, which means they don't point back straight to their sources, which makes it very difficult to directly detect the sources. But these kind of anisotropies should at least help in providing some idea about what their sources could be. And of course, if you go to higher energies, the deflections in magnetic fields become less. So you have more hope of seeing the sources directly, and at least seeing smaller scale anisotropies, which is what's shown here. Problem is as well, if you go to higher energies, that the flux drops significantly. So you also get just less statistics, which again makes it more difficult. So, okay, but yeah, what we want to do now is take all these different measurements together, and of course this is all happening at Earth, and we want to use all these measurements to say something about the sources of these particles, and that means you also have to know what happens in between those sources and the detection at Earth. And that's actually quite a lot for these ultra-energy cosmic rays. So after they are emitted by their sources, they travel through the universe, where they're first deflected by extragalactic magnetic fields. And they can also interact with different photon backgrounds. They can interact with the CMB and extragalactic background light. And in these interactions, all kinds of secondary particles can be created. So secondary cosmic rays, but also neutrinos and photons, or electrons and positrons, all kinds of different particles. And also in these processes, all kinds of unstable particles can be created. So you have to take nuclear decay into account before finally these cosmic rays arrive at our galaxy, where they are again deflected by the galactic magnetic field before finally arriving at Earth. So to use these measurements and say something about the sources, we have to model all this that's happening in between. And for that purpose, we have developed the code called CR-Propas. There's several other codes out there as well. But yeah, as one of the authors of this code, I would like to highlight this one, of course. So see, we are actually at the point of releasing a new version of CR-Propas. So if you're interested in this code, yeah, check it out. We have the website there with all the information, and it's just publicly available code, so anyone who wants to use it can just download it. And somewhere within the next week, the new release should come online. So what can you do with a code like this? We can try to explain the spectrum and composition of ultra high energy cosmic rays. And so yeah, the simplest way to do that is by assuming a continuous distribution of identical sources. Then you assume that these sources emit just a power law energy spectrum with a rigidity dependent cutoff. So exponential cutoff most of the time. So this is rigidity dependent. This means that particles with a higher charge get accelerated to higher energies, which is generally what you expect for cosmic ray acceleration, because most of the acceleration processes depend on magnetic fields in some way. So strong, yeah, larger stronger charge of the particles means that you get stronger deflections in magnetic fields, so that you can get accelerated these particles up to higher energy. And then you assume some kind of composition at the sources. Generally speaking, what is used is that you start with a certain number of protons, helium, something intermediate like nitrogen, and some heavier particles like silicon and iron. And you also have to make some assumptions on the evolution of the sources with redshift, which you can parameterize in some way. And then if you combine it all together and take the different free parameters like the spectral index, the maximum rigidity, and composition at the sources and the source evolution, and then use this to fit both the spectrum of ultra-energy cosmic rays and the composition of ultra-energy cosmic rays. And then generally speaking, what you get is a relatively hard injection spectrum, relatively low maximum rigidity, and basically the composition at the sources is somewhere between intermediate to heavy, and source evolution is rather unconstrained. And then, yeah, you get a figure that looks like this. So this is from work from a master student of mine, but this is some very similar studies have been done many times before. So I listed a few of those papers here, and they basically all follow very similar assumptions and to find these kind of very similar conclusions. So one other thing that you basically get for free if you do these kind of simulations is the cosmogenic neutrino flux that corresponds to these kind of fits. So cosmogenic neutrinos are the neutrinos that are produced during the propagation of ultra-energy cosmic rays, so not in the sources themselves, but really on the way in the different kind of interactions that occur. And unfortunately, if such a scenario is indeed what is happening, the cosmogenic neutrino flux is expected to be really quite low. So these are the neutrino fluxes that you would expect from such a scenario. And you see the ice cube measurements here, and the current limits are there. And then these are proposed sensitivities for ice cube Gen 2 radio grants of very impressive projects. But unfortunately, these will not even be sensitive enough to detect these neutrinos. So yeah, this would really be quite a disappointing scenario if this is indeed what's happening in nature. So we get really quite few neutrinos, cosmogenic neutrinos at least. And also, if you look at this figure, so here the different lines show different mass groups, and at the highest energies, you only have very heavy particles. So this is also quite disappointing, because this means that these heavy particles get strongly deflected in magnetic fields, which means it will be more difficult to do just ultra-high energy astronomy with these particles. If you have, say, protons at these highest energies, you can still expect that they point back to the sources. But if you have only iron at these highest energies, then the deflection will be quite strong, and it will be quite hard to see these sources. Now, so the question is if this is really what is happening in nature. Well, I would at least argue that this setup is really quite simplistic. So it's basically the simplest thing that you can do. The assumptions that are followed here is that you have a continuous distribution of identical sources, which is of course not what is happening in nature. We don't have a continuous distribution of sources. No two sources are identical, let alone that all sources in the universe are identical. It would be very strange that if, say, all sources accelerate particles to exactly the same energy. And of course, one of the other assumptions here is that you have a rigidity dependent of maximum energy, which is in principle a fine assumption, but not necessarily true for all sources. It really depends on the specific source assumptions and source setup. And if you look at these two assumptions, if you assume that all sources have the same maximum rigidity and you have a rigidity dependent maximum energy, then you will automatically get a scenario like this, where you cannot get any protons at the highest energies, because you need a relatively low maximum rigidity at all sources just to get this trend of getting heavier with energy, which means that you cut out all the protons at the lowest energies. But the question is this really realistic or not? So what you can do is actually add an additional source population to these kind of fits. Source population produces mainly protons. You can add heavier things here as well, but as long as they're subdominant to the proton component, and they won't affect the fit results too much. And the idea of this additional source population is that you have additional sources with so either really a different kind of sources that just can accelerate cosmic rays up to much higher energies, but produce a subdominant component compared to what is happening in the intermediate energy range. Or you could even have basically the same sources, but variation in the same source class by having different maximum energies there. So yeah, so that there will be some sources at least that can accelerate cosmic rays up to higher energies than just this under this very basic assumption that all sources have the same maximum energy. So if you do that, if you add such an additional source population to the fit, then what happens is something like this here for the fit. You get this gray line here, which is just a pure proton line. And you can still get a very good fit to the spectrum and the composition. It's actually very good chi-squared you get out. You actually get quite a lot of protons at the highest energies, which would be really interesting for these kind of anisotropy studies. And if you now look at the neutrinos that come out of such a scenario, then you basically cover this entire band here. So this is so large because the source evolution with redshift is basically unconstrained. So ultra-high-energy cosmic ray measurements cannot say much about source evolution with redshift because all the ultra-high-energy cosmic ray sources are relatively nearby. Because of all the energy losses that happen in between the sources and Earth, they cannot come from, and the ultra-high-energy cosmic rays themselves cannot come from too far away. But the neutrinos can, of course, come from very high redshifts. So this means that these cosmic ray measurements cannot tell you much about source evolution, which gives you a large uncertainty here in the expected cosmogenic neutrino flux. And you can see that this under this assumption with this additional proton component, you get neutrino fluxes that even go above the current neutrino limits, but can also be still quite low and difficult to detect later on. Yes, there's a question. Federico?
Hi, yeah, so my question is about the source evolution. Why do we expect the source evolution to be so unconstrained? I mean, do we have a model for how much sources should change? And also, like, all of these cosmic rays are so close to us. Do we really expect the sources to change so much between here and 100 megaparsec or 200 megaparsec?
No, exactly. That's kind of the point. So we don't expect this source evolution to have a strong effect on the cosmic rays at all, because they are also nearby, indeed. So, but we also have faraway sources which do produce neutrinos and produce cosmogenic neutrinos because they do produce cosmic rays. We cannot see those cosmic rays because they never arrive at Earth. They're too far away for that, but we can see the neutrinos that are produced by those faraway sources. So, and generally speaking, this such source evolution, and I mean, because we don't know the actual sources of these cosmic rays, we just model this source evolution in a very general way. And so so something like this, which just 1 plus the redshift to the power m up to a certain redshift, and then flat after that, where in this case this goes up to a redshift of about 4 maximum. And then you can take this value of m here somewhere between -6 and +6, use a very large range for that. And in this way, you can roughly describe all kinds of different source classes that follow different kinds of redshift evolutions. But indeed, just by looking at the ultra-energy cosmic ray measurements, this value of m of the source evolution is basically not constrained, just because it doesn't really affect these cosmic rays so much. You get a small effect at the lowest energies, because the lower you go in energy, the farther away these cosmic rays can get to you. But especially at the highest energies, everything will be from 1 to 200 megaparsec. The lowest energies, you can still get like results from redshift of 0.5 or something like that. So this it depends a bit. So it has a small effect, but it's basically if you can fit all kinds of different source evolutions to, at least if you just look at the spectrum and composition. So that's why one of the reasons why it's also interesting to look at the neutrinos and see what comes out there, because they very strongly depend on what kind of source evolution you assume here. Did that answer your question?
Yes, thank you.
Yes, great. So okay, if you now add such a proton component, so you improve the quality of the fit, you have possibly more realistic assumptions, and you significantly enhance the cosmogenic neutrino flux, and you actually get some protons at the highest energy. So I think it's quite interesting scenario to consider. Yeah, and you get these large uncertainties basically because this source of evolution is unconstrained. Now, if you take this one step further and look which parameters actually make it so that you get such a large cosmogenic neutrino flux, then the two parameters that are important are the diffraction of the protons and the source evolution parameter m. All the other parameters only play a minor role in determining the value of the neutrino flux. So so what this plot shows is that if you have a neutrino flux of this level, 10 to the minus 8 in these units, then you expect to be somewhere here in this range in the combined parameter space of source evolution and proton fraction. So the current limits of Auger and IceCube at 10 to the 18 electron volt are at the moment at this range. They did not see any neutrinos at 10 to the 18 electron volt. So that means that this top right part of the plot is actually already excluded. So we know that we cannot have a very large proton fraction and very strong source evolution. And if we now go to future generation neutrino detectors, then with IceCube Gen 2 radio, we're somewhere in the middle between these two ranges. So this is an order of magnitude better in neutrino flux or more sensitive. And this is again another order of magnitude lower. And with IceCube Gen 2 radio, you expect that you can really probe this parameter space very well. So, and if you now look at what this actually means for specific source candidates, then we can put specific sources here. And we know, for example, that high luminosity active galactic nuclei, which are a very interesting source candidate class for ultra high energy cosmic rays. They're basically the most extreme sources, or at least continuous sources that are out there. They have a really strong source evolution with redshift. So they are, with the current limits, already strongly constrained. At least the proton fraction that comes from them, it's already quite strongly constrained. And this means that later on with future neutrino detectors, we can detect even very small proton fractions coming from sources like that. If you now go to very regular sources, regular galaxies, then they follow this star formation rate. And we are here at this line. If you go to 0, we are just a co-moving source evolution. So so you can see here that you're probing very interesting parameter range, which covers most interesting source candidates for ultra high energy cosmic rays. So now the question is, if this is if such a combination can be expected of two different source classes or an additional proton component from a same source class in this direction. So one scenario where this comes out quite naturally is if you look at active galactic nuclei as possible sources. So what we did for this study is we simulated not only the interactions during the propagation of ultra high energy cosmic rays to their sources, but also the interactions inside the sources themselves. So what you get then is the predictions for both source neutrinos and cosmogenic neutrinos. And we divided up active galactic nuclei in 3 different subsets. So low luminosity BLX, high luminosity BLX, and FSRQs. For BLX are basically more dominant, more abundant sources, but less intense, less active. Relatively smaller sources than the FSRQ. So these are FR1 radio galaxies compared with FR2 radio galaxies. BLX have a relatively low photon density, while FSRQs have a higher photon density. So this also means that you have 2 different types of sources, a low photon density means that you have very few interactions inside the sources themselves, which means that you can actually quite efficiently emit ultra-energy cosmic rays without them interacting inside and losing energy inside the sources. But this also means that these sources are relatively inefficient neutrino emitters, because you actually need interactions inside the sources to produce neutrinos and to emit neutrinos. And so what you would expect in this case is also in these rigidity-dependent maximal energies, which we saw earlier, just because you accelerate ultra-energy cosmic rays up to high energies without them actually interacting. And then we have the FSRQs, which have a high photon density, which means that they are quite efficient in photohadronic interactions, which means that they produce abundant numbers of neutrinos, but they also emit only light ultra-energy cosmic rays, because the heavier cosmic rays interact inside the sources, fall apart, and only the lighter ultra-energy cosmic rays escape the sources. So very shortly, what you see then is something like this. You can explain the cosmic ray flux and composition, and if you then look at the neutrinos, then you actually get really quite a large number of source neutrinos out. So here the flux is mainly produced by low luminosity BLX, which gives you the heavy composition with increasing energy. And then there is a subdominant component of FSRQs, which mainly gives you a light cosmic rays. But in the neutrinos, it's the other way around. You get a lot of source neutrinos, which all come from these FSRQs. And this is actually, so the contribution of FSRQs to the ultra-energy cosmic rays is here constrained by the limits of by the neutrino limits that are given here by IceCube. So what is quite interesting to see here is that these source neutrinos can actually outshine the cosmogenic neutrinos even. So depending, of course, on your assumptions and on the specific scenario. But this means that you can even, at the highest energies, expect a significant amount of source neutrinos, which will also be very interesting to see, which means that you can possibly, if you indeed have source neutrinos there, that means that you can possibly identify and disentangle these kind of source neutrinos with different techniques, so stacking searches, flare analysis, and so on, things that you cannot do with cosmogenic neutrinos because they're deflected on the way, only produced on the way, and probably do not point back to straight to their sources. So, but for now, okay, I've been talking only on spectrum and composition and on neutrinos. So now let's also have a look at the arrival directions of ultra-energy cosmic rays. So I also thought to you in the beginning that we have several indications of anisotropy in arrival directions found by the Pierre Auger Observatory. So this is the map I showed you in the beginning. So now if we zoom in a bit here, we have a hotspot here where we have several interesting source candidates right in the center. So one of them is SEN-A, which is a nearby AGN, which could produce this hotspot. But there are also these three yellow stars here, which are NGC 4945. This is Cercinus and this is M83, which are three different starburst galaxies or star-forming galaxies, which are in this also in this part of the sky. And then there is one other star-forming galaxy, NGC 253, right here in the south, which is also in the middle of this hotspot in the south. So Auger has done several analyses on these sky maps, trying to see where they get the largest significance for correlations, and what they found is basically summarized in this table here. So the highest post-trial significance is for starburst galaxies, which is 4.5 sigma, and the different catalogs of AGN also get up to about 3 sigma. the main difference is really this one source here, NGC 253, which is in the south and can explain this hotspot here, while there is no nearby AGN in this area. So what you can do with these results, and this is in my opinion really quite interesting, is that you can use them to say something about the magnetic fields that are in between these sources and Earth, and you can and about the local density of sources. If we look closer at these results that Auger reported and focus on the starburst galaxies only, then we see that they give a value for the parameter theta here, and this theta is the optimal angular width around the sources. This is a measure for the deflection of ultra-high-energy cosmic ray from the sources. And then there is this parameter F aniso here. So this is the fraction of ultra-high-energy cosmic rays from the catalog sources compared with an isotropic background. In this case, this is about 11%. And you can imagine that a large local source density means that you have very many sources that are contributing to your ultra-energy cosmic ray flux, and yeah, many sources contributing means that you reduce the expected level of anisotropy. So this parameter F aniso is really a direct measure of the source density of the background sources, at least of these ultra-energy cosmic rays. So we try to analyze these results of Auger and see what we get out for limits on the strength of the extragalactic magnetic field and the local source density. So basically what we did is we simulated ultra-energy cosmic ray sky maps for specific extragalactic magnetic field and galactic magnetic field setups and local source densities, and then checked if these maps give this theta and F aniso values that are compatible with what Auger found. So very shortly. So we focused, and in a bit more detail, we focused on the four most important sources only, because they are really the nearby ones and give more than 90% of the actual signal. Then we use these kind of fits to spectrum composition. We simulated the deflections in extragalactic magnetic field and galactic magnetic field for different values of the extragalactic magnetic field and one model of the galactic magnetic field. And then we combined this with catalog, and these catalog sources, results from catalog sources, with an isotropic contribution from background sources, following a specific source density, and the source density then determines the relative contribution from the background sources compared with these catalog sources. And then what you get out are sky maps that look like this. So these are all for the same extragalactic magnetic field, but for different source densities. So I'm just showing two extreme cases here. So this is for a very low source density, and then you get a very strong correlation with the catalog sources. This is for a very high source density. You basically get an isotropic sky. And the top two plots are without deflections in the galactic magnetic field. So if you now turn on the deflections in the galactic magnetic field, then you get these two figures here. So you see that the galactic magnetic field really strongly can strongly deflect the different particles, and due to this, you already significantly reduce the observable anisotropy. Now, if you do this in a systematic fashion and scan over the different values of the extragalactic magnetic field strength to different local source densities, do this for extragalactic magnetic field only and for extragalactic magnetic field plus galactic magnetic field, then you get these kind of results. We do this both for with and without the galactic magnetic field, because of course we don't perfectly know what the galactic magnetic field looks like. And this is just one specific model. So we want to scan the a larger possibility range just by both including and not including the galactic magnetic field. Of course, with the galactic magnetic field, it's a more realistic scenario, but there are large uncertainties on the galactic magnetic field itself. And so what you get from these cases is if we have a local density of star-forming galaxies, you need a relatively strong extragalactic magnetic fields to agree with the measurements of Auger. Or you can go to rather large local source densities, but then you get to source densities of spiral galaxies, which are quite hard to explain. So let me wrap up a bit.
Arjen, so we have a question.
Yeah, go ahead.
So it's me again. What are these strange units about this magnetic field?
This is because
what is this like megaparsec to power half?
Yeah, this I skipped over here. So this is because this parameter that we show here is actually not just a magnetic field strength, but it's a magnetic field strength times the square root of the coherence length. We use this because this is actually, in principle, you have both the magnetic field strength and the coherence length that you have to take into account for these magnetic fields. But what actually influences the deflections of cosmic rays is the magnetic field strength times the square root of the coherence length. So you can see, of course, stronger fields give you stronger deflections, but a longer coherence length of these random magnetic fields also gives you stronger deflections because you have a continuous deflection in the same direction along a longer distance. So what is important for the amount of deflections of ultra energy cosmic rays is really this combination of parameters. So that's also why we call this like B tilde here. So this is not really a magnetic field strength. So it's a magnetic field strength for a coherence length of 1 megaparsec. But this is really the combination of magnetic field strength and coherence length, which is what influences the amount of deflection that you expect for ultra energy cosmic rays.
And sorry, and these fields are like all pervaded; they're everywhere, right?
They're everywhere.
Like everywhere.
Yeah. So we.
And how do these fare with like limits we had from I don't know, rotation measures, etc., etc.?
Yeah. So that's
how far away from those limits.
Right. So that's a bit difficult to say because there are general limits on extragalactic magnetic fields in voids, which are about 1 nanogauss, roughly. It should be lower than 1 nanogauss. In that case, this would be okay, but this is not, for example. But those are extragalactic void fields, and it's not really fair to compare these results with that because this describes the extragalactic magnetic fields between those 4 nearby sources and the Milky Way, and those sources are within 5 megaparsec from us, so it's really quite nearby. So you cannot really expect the extragalactic magnetic fields just to be void fields in between those sources and Earth.
I was more referring to the rotation measures, like the just sub nanogauss from CMB and rotation measures, right? I mean, they like especially rotation measures are not so far.
So I think for that, this is still perfectly compatible, but I also don't think this is because I think we're in that case we're also at least I wasn't able to find specific limits on the extragalactic magnetic field for rotation measures in the specific directions for these very specific really local distances. So it's really quite hard to compare this specific properly.
Okay, thank you.
Okay, so I should probably stop soon. I'm guessing I'm running out of time. So at least what we concluded from this is that you need relatively strong extragalactic magnetic fields to agree with the measurements of Auger. If indeed you have a local source density of star-forming galaxies, you can go to larger local source densities, but then you get up to local source densities, for example, of spiral galaxies. And it's not really expected that such abundant sources as spiral galaxies actually produce ultra high energy cosmic rays. So yeah, you have to either go to strong, relatively strong extragalactic magnetic fields or large source densities, which are hard to explain from an acceleration point of view. You also get upper limits, but 90% confidence level upper limits on both the magnetic field and the source density in this case, because a larger source density, a larger magnetic field means that you actually wash out the anisotropy signals that Auger observes. This is not at the 5 sigma level, because also the results of Auger are not at the 5 sigma level, so you cannot get very strong constraints on this yet, but at least at 90% confidence level, you can already get some constraints there as well. So very short summary, we have ultra energy cosmic ray spectrum and composition fits under the simplest assumptions. These fits produce very low cosmogenic neutrino fluxes, but you can improve these fits by adding an independent proton component. You get much more cosmogenic neutrino fluxes, you get a better fit, perhaps more realistic assumptions. And if you now also include source neutrinos, then depending on the specific sources that you're looking at, these source neutrinos could even outshine the cosmogenic neutrinos and are also definitely interesting to look at. And if you include now arrival directions as well, then you need either relatively strong extragalactic magnetic fields or rather large source densities to explain the results of Auger. Thank you.
Questions? Yeah.
Yeah.
Can you hear me?
Yes, perfectly.
Hello. Well, thanks a lot for the nice talk. Yes, a couple of curiosities because I know nothing about this basically. So you produce this large of neutrinos and also antineutrinos. Is the same things or is it?
Yes. So you produce. Yes. Sorry.
Go ahead.
Okay, so yeah, you produce, so the main interaction that produces neutrinos is photopion production. So you just have pion decay and muon decay that produces these neutrinos. So you get electron neutrinos, muon neutrinos, and both antineutrino and regular neutrinos in there. And then of course you have neutrino oscillations later on. So you get in the end, all different types of neutrinos at Earth. And in these kind of predictions here, we basically group all the antineutrinos and neutrinos and all the 3 flavors together. But you can easily split this up into the different types of neutrinos as well. And I think we have a talk on probably more information on that later on from Mauricio's talk.
All right, and how natural it is this flux that you show at the end in your slide, in your conclusion slide? You have the, well, I don't know if this is the same, but there is this blue dash line. You say that if there is a source, is this a kind of natural assumption that there is such a source, or is? Yes.
Yeah. So this is I can explain it better with this slide. So this this blue line depends on the how much the FZQs contribute to the ultra energy cosmic rays. You see that there are, in this case, already they're subdominant. So basically means that, but they completely produce this neutrino flux. So that means that basically your ultra energy cosmic ray measurements are decoupled from your source neutrinos because they're produced in different sources, at least dominantly, than these neutrinos. Which also means that one of the basically parameters that you don't really know is in modeling these sources is the baryonic loading, and this baryonic loading basically gives you how many cosmic rays you will get, and so also how many neutrinos you will get. So this is and kind of a free parameter in here. what we did here is we pushed these FSRQs up to the highest allowed value that is still okay with cosmic rays. So and with the current neutrino limits. But it could also definitely be less, that everything is just produced by, so all cosmic rays are just produced by BLX, and you have much less produced by FSRQs. So you also get much less neutrinos out. So this is really an upper, I mean, you could push it further if you ignore the current neutrino limits, but this is like the upper case that is allowed by the current neutrino limits and cosmic ray measurements.
So in a pessimistic attitude, then this could even be below the cosmogenic and everything. It
Yes.
could not be, okay.
Yes, indeed. So I think I even have a backup slide on that. Let me check. No, sorry. Too many backup slides. That one. Here. So this is basically the allowed range now that you get for neutrino fluxes, where the blue ones are the source neutrinos and the brown ones are the cosmogenic neutrinos. And you see that, yeah, you cover quite a large range, which is allowed. And this, the top line is the same line that I showed earlier. So this, just shows that unfortunately, this is quite uncertain. We could be very close to measuring these neutrinos, but could also still be quite far away.
Any more questions? Zoom. One more question.
Arjen, one question about your second proton component that you were showing early on. Would that not induce also an anisotropy?
Yes,
like, shouldn't those protons point back to the sources better than the nuclei?
Yeah.
And maybe I missed that. Yeah.
Yeah, so I didn't actually say anything about that, but yes, indeed. And that's a very good point, and thank you for asking. So what we assumed here in these kind of figures with these limits is just the regular scenario without this additional proton component. So if you now have additional protons produced at these sources, then protons are deflected less than the heavier nuclei, so you get less deflections in magnetic fields, meaning that you get even stronger limits on the magnetic field. So this is the more conservative limit in that case. So what would happen? So basically, if there are indeed also protons at higher energies produced in the same sources, you would need stronger magnetic fields to get the same anisotropic results. But a kind of idea of this additional, at least what this additional source, this additional proton component could represent, is an additional source population of a source population of different sources that produces this, more extreme sources that can accelerate cosmic rays to higher energies. So in that case, you would not get these protons from the same sources as you see these correlations with. So you would get them from rarer sources, so less abundant sources that are farther away and less, and therefore cosmic rays are deflected more because they're farther away, and so they're more difficult to see. Especially because you cannot do now an event by event determination of the composition of cosmic rays. Once you are able to do that, which is what the Auger is planning with the upgrade that they're doing at the moment, where they can kind of say on an event by event basis whether a cosmic ray has a light composition or heavy composition. So once you are able to do that, then you can really do this kind of astronomy with these protons and trying to point back and see where they came from.
Thank you.
Okay, so let's thank Arjen again for a very nice talk.